Hello everyone. Today we are going to solve the governing differential equation of a cantilever bar subjected to uniformly varying axial load. But before we get straight into the business of solving the governing differential equation, I would like to emphasize the importance of governing differential equation. Governing differential equation helps us to predict things just like a palmistry. There is a mathematical explanation to everything in this universe. Everything is governed by governing differential equation. The father of string theory, Leonard Susskind, says that almost everything in this universe actually boils down, if you represent it mathematically, to governing differential equation. Let us watch the statement by Leonard Susskind, the father of string theory.
It almost always has to do with differential equations. Let me take back one phrase. Almost. It always has to do with differential equations, yes. It may be that other things, other mathematical things are more important than the differential equations in this particular area or that particular area, but it always has to do with differential equations.
So whether you were investigating the elementary particles or you were talking about the expansion of the universe, there is a language associated with it. That language is governing differential equation. So governing differential equations are of cosmic importance. Let us solve the problem of a cantilever bar subjected to uniformly varying axial load. Okay, now let us solve the governing differential equation of a cantilever bar that is subjected to uniformly varying axial load. Okay, let me first draw a cantilever bar. So one end of the bar is encasted into the wall. Okay, we have got a cantilever bar. Let me define the geometric properties of this cantilever bar. This cantilever bar has got a length of magnitude L. It has got a cross-sectional area of magnitude A. So I have clearly defined the geometric properties. Let me define the material property. This cantilever bar is made up of material that has got an Young's modulus value of magnitude capital E. Now, what is the stuff that is acting on this bar? This bar is subjected to uniformly varying axial load. So something like that. So you can see that the arrow mark keeps increasing in its size. It means that the rate of loading actually increases. And the magnitude of the rate of loading is Qx. And its unit is Newton per meter or Newton per mm, depending on whatever unit is conducive for you. Now we have already derived the governing differential equation. So let me write the governing differential equation here. It is AE into d square u over dx square plus qx is equal to 0. So that is the governing differential equation. Okay, now let me define the boundary conditions. What is the first boundary condition? One boundary condition is obvious. The displacement at the left extreme end is going to be 0. The second boundary condition is the strain at the right extreme end is going to be 0. The reason why strain at the right extreme end is going to be 0, I have given that explanation in the previous video. Please watch the previous video in order to wrap your mind around how we actually get these boundary conditions and this differential equation. Okay, what is the first step to solve the differential equation? What are the steps that we are following? The first step is to assume a trial solution. So here we go. Assume a trial solution. So what is the trial solution that we are going to assume? Okay, let me take this boundary condition. I'm sorry, the governing differential equation. It is AE into d square u over dx square plus qx is equal to 0. That is the governing differential equation. What I'm going to do is I want to find u, that is displacement. What is the displacement? How do I find this u? How do I find an equation for u? What you have to do is you have to integrate this governing differential equation 2 times. So first let me integrate this equation 1 time If I integrate this equation one time, I'll be getting du over dx. And if I integrate this qx, I'll be getting qx square over 2 plus the constant of integration, that is equal to 0. Now integrate this equation again. It is ae into u plus q into x cube over 3. So 3 2s are 6 plus c1x plus c2 is equal to 0. I'm interested in finding u. So I'm interested in finding this particular u. So I'm going to do it in one go. I'm going to take every other term to the right hand side in order to find u. So let me do that in the next step. So here we go. U is equal to, so take every other term to the right hand side. It is going to be minus c2 minus c1x. Okay, it is minus c2 minus c1x minus qx cube over 6 minus qx cube over 6. Of course, we have to divide each and every term by ae. c1 over ae, q divided by 6 over ae. Now I'm going to rewrite this equation as u is equal to, what I'm going to do is I'm going to call this term here minus c2 by ae as a naught, and I'm going to call this term minus c1 divided by ae as a1, and I'm going to call this term as a3. I'll tell you the reason why we are not writing a2. So the type of equation that I will be getting here is, the above equation now becomes a naught plus a1x plus a3 x cube. Now you obviously know what happened to that a2. a2 is 0. You can even write this equation as a naught plus a1x plus a2x squared, but x squared term is not there, so a2 should be 0 plus a3 x cube. So this is going to be our first trial solution. This is our trial solution. So the first step, the trial solution, that is over. We have got the trial solution, which is a naught plus a1x plus a3x cube. If you know the values of a naught, a1, a3, then the problem is over. Now let us do the second step. Second step is to apply the boundary conditions. So let me apply the boundary conditions. So I will write that. The second step is to apply the boundary conditions. What is the first boundary condition? We know what is the first boundary condition. That is, the displacement at the left extreme end is 0. That is, u of 0 is equal to 0. If you reflect this particular boundary condition on this particular trial solution, this equation, at x is equal to 0, a1x, this term becomes 0. At x is equal to 0, this term becomes 0. At x is equal to 0, u should become 0. So what will happen to this equation? You say u becomes 0, so 0 is equal to a naught plus 0 plus 0. So a naught becomes 0. So that is what we get when we apply the first boundary condition. Now I'm going to apply the second boundary condition. So here we go. Let me apply the second boundary condition. The second boundary condition is the strain, which is du by dx. At x is equal to L is going to be 0. So first let me find du by dx. Du by dx is equal to a1, if you differentiate this equation, u, a1 plus 3 a3x square. So that is what you will be getting for du by dx. And du by dx at x is equal to L becomes 0. So du by dx becomes 0 at L when x becomes L. So 0 is equal to a1 plus 3a3 L square, because it is at x is equal to L, the value of strain becomes 0. So I'm getting another equation. I'm getting A1 in terms of A3. So A1 is equal to minus 3A3 L square. Now I got the value of A0. So here we go. I got this value of A0, which is 0. I got the value of A1 in terms of A3. So what I can do now is I'm going to substitute the value of A0, A1 in terms of A3 in this particular equation, and let me modify the trial solution. So in the next step, which is going to be step number 3, I'm going to modify the trial solution. For my convenience, I'm going to modify the trial solution. So step number 3, I'm going to modify the trial solution. So modified trial solution. Modified trial solution. So here we go. What is the modified trial solution? U of x is equal to A0 is 0 plus, what is the value of A1? A1 is minus 3a3 L square. So A1 is minus 3a3 L square. A1, excuse me. A1x plus A3x cube. That's that equation. I'm sorry. A3x cube. So I can rearrange this equation as U of x is equal to, you take A3 common outside. The equation that you will be getting is x cube minus 3L square x. All you have to do is find the value of A3. Then the problem gets over. So I will put a nice box here. All I have to do is find A3 and everything will be over. So in order to find A3, I'm going to do step number 4 here. Step number 4 is find the value of d square u over dx squared. Why do I want to find this? Because that is what is demanded in the governing differential equation. You look at this governing differential equation, d squared u over dx squared is what is demanded in this governing differential equation. So once I get the value of d squared u over dx squared, I simply have to substitute that value in this equation. And let me see if I can turn the crank of mathematics and find the value of the constant. Okay. What is d squared u over dx squared? Differentiate this equation 2 times. If you differentiate, this is the equation for u. If you differentiate this expression 2 times, this term will become 0. The second term is going to become 0, this term. What about the first term? If you differentiate 1 time, you get 3x squared. If you differentiate 2 times, you get 6x. So 1 time differentiation, it is going to be 3x squared. 2 times the differentiation, you will be getting 6x. So it is going to be a2 into 6x. You get, I'm sorry, it is a3 into 6x. Okay, I got the value of d squared u over dx squared. Okay, let me substitute the value of d squared u over dx squared in the governing differential equation. So that will be step number 5. Step number 5 is substitute d square u over dx square in the governing differential equation. So let me take the next page and let me substitute the value of d squared u over dx squared. So governing differential equation is ae into d square u over dx square plus qx is equal to 0. The next step, it is going to be ae into d squared u over dx squared. That is 6a3x. So it is going to be 6a3x plus qx is equal to, should I put 0 or should I put r? Should I put 0 or should I put r? I can put 0 because the reason why I can put 0 conveniently here is because if I put 0, I can find the value of A3. If I find the value of A3, it is going to be minus Q over 6AE. That is what I am getting. I got the value of A3. Now you may ask me this question. Usually we substitute R here. Now how can you put 0? We put R only when you are finding the value of constant in terms of a variable, when you put 0. Here the constant A3 is not in terms of a variable. Here the constant A3 is completely a constant. It is not a variable. So we are on the safe side. You don't have to apply point collocation. You don't have to apply subdomain collocation. You don't have to apply Galerkin's weighted residual methods, because the constant that you have got here is not in terms of a variable, so it doesn't need other methods like point collocation. It doesn't need subdomain collocation. It doesn't need Galerkin's weighted residual. So you have got this value of constant, and you can now substitute the value of constant in the modified trial solution, and you can get the final equation. Now the last step here, which is going to be step number 6, you have to substitute the value of A3 in the modified trial solution. So what is the modified trial solution? So here we go. The modified trial solution is here, this one. So u of x is equal to A3 into x cubed minus 3l squared x. U of x is equal to A3 into x cubed minus 3l squared x into x cubed minus 3l square x. You just substitute the value of A3. U of x is equal to A3 is minus q over 6a into x cubed minus 3l square x. So I can rearrange this equation as u of x is equal to q over 6a into 3l square x minus x cubed. So I have kind of retracted the minus sign. Outside, if you just bring one more minus sign outside, it becomes plus q6 over l 6a. I'm sorry, plus q divided by 6a into 3l squared x minus x cubed. Okay, that is the solution.